Ready to continue? Let's let everyone settle back in. I'm gonna get back going, guys. So what do we have here? We have a system that's a generative art system that's being controlled by my face. So it's not terribly exciting yet, but we have a template, right? We can make this, you know, like if you can connect this back to your previous knowledge of processing classes and learning generative art, and you could easily make this look a lot cooler. So watch how fast I can make this look cool. So I'll say, let's first of all make this bigger. Now one problem, if you know much about the noise function, is that it's a little jumpy. So as I move around, it's like very jumpy, right? One way of fixing this would be a tiny change to this code where instead of doing r times I, we are going to create a new variable called, let's call it AMT, like amount, and then let this be AMT, well, let's see, what would be the best way of doing this? Hang on. AMT, and let's do AMT comma I times 0.01, and then AMT at the end of draw, AMT plus equals R. I think this should work. Let's see how this looks. Okay, it's a little jittery. Still a bit jittery. So I think maybe if this should be AMT plus 0.1 times R. And actually, let's make this like 0.1. Faster, slower. Faster, slower. Here's another cool thing you can do. Instead of drawing the background, let's clear this background and we'll say fill 0 like 30, and then rect 0, 0 width height. Now it'll kind of accumulate to the screen. Have a little bit of a fade there. Maybe make it like 0, 10. Now it looks a little bit like that cover of, what was it? Was the Talking Heads? No. What's that album cover? Everyone, what's that? Joy Division, yeah. This looks like the Joy Division chart, right? This might also look better if we do, instead of vertex, do curve vertex. It's a little smoother, although it might also get slow. That's not too bad. Small differences. Or we can say n equals 10 instead of 100. Now it'll be a lot smoother. A little too smooth, actually. So maybe make this I times 1. Maybe it should be like 30. A little medium. Anyway, you get the basic idea, right? It's kind of neat, right? Can make this a little bigger, 600 times that. So basically, like, the more you learn about how to make generative art, the more you can start to think about how I can grab one of the parameters that controls what my program looks like and connect it to one of these sliders, right? So that's the basic idea. Okay, so let's do something a little bit more complex and fun. We played. So remember on the first night we did the T-Rex demo. So we can actually code that so that you can control your own computer. The question is, what game do we want to play, and how do we want to control it? Well, we can use what we have right now. We can use the face classifier. That might be a little tricky because, okay, so you'll go like in front of it and it'll, I think maybe it'll make sense to use the camera input. So here's what we're going to do. First of all, we can switch gears and go to move on. First of all, are people still copying? So maybe I'll just let you guys get those last changes, and then eventually I'm going to close this and make something else. So how many people are still want this on the screen? Okay, so I'll leave this on the screen for a moment. So everyone's got that? Cool. Can I continue? All right. So I'm going to close this, or I'll just minimize it if anyone needs it later. So we'll have it there. So I'm going to get out of the faces, and I'm going to open another processing sketch. Now, okay, so we can do this with the sound classifier, right? But the problem is that we can't all do it at the same time, because it's very sensitive to sound, and so there's too many of us making sounds for this to work properly. So let me actually just show this to you so you have it, because this is one of the inputs that's available to you if you want to use. So there's two of them actually. There's a sound classifier, and then I think this one is a little bit simpler. Sound 14 inputs. This sends to Wekinator 14 values which characterize the frequency spectrum of the sound that you're making. So you see I can be like, hello, ooh. Okay, so it's sending different values, and it's sending 14 values to Wekinator. So you could train a sound classifier or a sound regressor or something like that. And then actually this one I think maybe does classification straight up. So let's see. This one I haven't used yet, so I don't even know if this one you might need to install minim if it doesn't work for you, I think. But let me see if this, oh. Yeah, oh, Control V5 doesn't work in this processing. I'd have to update. Okay, I won't look at that. So there's, you could probably run that if you just install Control P5 and minim. But that one is a more advanced sound classifier. This one should work. I think, if this doesn't work for you, you have to go to Sketch, Import Library, Add Library, and search for minim, M-I-N-I-M. And then there's this library, minim and audio library, so you have to install that, and then that sketch will work for you. Okay? But I'm not going to actually use that sketch right now because it's too complicated for all of us to train the sound classifier in here, because we're going to be hearing each other, so that will get complicated. So instead, what I want to do is I want to open up the basic video classifier. Just notice, by the way, there's a bunch of things here that we're not going to look at today because we don't have time and we don't have the equipment. But if you have, for example, a Leap Motion is a tiny device that's hand tracking. It tracks your hand and the fingers and stuff. I think it's like $100 US or something like that. You can get one online, and it tracks the position of your hand. And so there's a input here that lets you take that and use that as your, there's a program here that lets you use that as your input to Wekinator. And there's also one for the Connect. So for anyone here who has a Connect, you can upload the depth image. And for people doing Arduino stuff, anybody here use Arduino? Okay, handful. So there's some Arduino code, and you can use Arduino as an input as well. So I'm going to open video 100 inputs. So this is the same thing that we looked at in the beginning, the 100 inputs, but all it is just the input. So it doesn't have the classification, it doesn't receive from Wekinator, it just takes the grid of 100 pixels and uploads that to Wekinator. So you see it's sending 100 inputs to port 6448 with Wek inputs. So let's go into Wekinator. Let's get out of this. I'm going to create a new Wekinator project, which will receive 100 inputs on port 6448. So /wek/inputs, 100 inputs. And then the OSC message will set the number of outputs to be 1 and set this to be all classifiers. And let's say we'll leave it at 5 classes. Okay, so make sure you have this configuration. Then click Next, and you should get Wekinator up here. Now let's train a basic, like a simple classifier that will say, okay, when I'm here, let's say, this will be class 1. So start recording, record a bunch of examples for class 1, stop. And then I'm going to move over here. I'm going to move class 2. So recording 2. Now do one more thing actually. Go into edit here. And if you click on the edit button here, the thing is that right now we're using k-nearest neighbors, which is a classifier which is really not very accurate. So I want to actually change this. You click the little pencil next to k-nearest neighbors. So for those of you who didn't catch that, there's a little button here, Edit. So click that, and then you'll bring up this screen. And then it says, where it says Model k-nearest neighbor, click that, and change this from k-nearest neighbors to support vector machine. Okay, and you can leave everything else at the default settings. So now it should say model type support vector machine. This will make it a little bit more accurate. Apply changes, and once you've applied changes, click train, and that will train. Once you've hit train, you can click run, and now it's classifying. So that's 2, 1, 2, 1, 2, so on, right? Okay, so let's do something fun with this, right? We've got 1s and 2s, okay? Let's have Wekinator send its values to this thing right here, robot key press 1 output. So we're gonna have Wekinator control your keyboard. So if you open robot key press, and this will say, okay, so let's just see how this, yeah. Okay, so basically, right now, the way it's set up is that current class is 1, it does nothing. And then and in current class 2, it will actually hit the X key on your keyboard. So basically, if you run this, and then have so that's this, oh sorry, so let's have everything up top. So there's my input, there's the keyboard press, and let's have Wekinator visible. Last message 1, 2, 2. Every time it has 2, you notice in your console, it types X. It's actually hitting your keyboard. So let's actually have it do something else. How about this? Instead of the X, we'll have it press the spacebar. So go down, you see where it says current class equals 6, and it goes robot press key event VK space. Just copy this key event.vk space and copy it and paste it into class 2. So instead of VKX, you just do VK space, right? Or you can just edit that manually. So it should say key event for current class 2, key event VK underscore space. And now run that again, and now it's going to be hitting your spacebar. So you can tell, because you see if I go into the URL bar and then I move to the, oh, it should start hitting the spacebar, I think. Hang on a second. Oh yeah, see what it does? It just hits the spacebar. Hits it once. Okay, so not terribly interesting, but what we can do is, if you search for T-Rex game, now you can try to make the dinosaur jump. So you always have to go back left. So like to class 1 and then class 2. Okay. So obviously this is like going to be very, it's going to make me dizzy. Oh. Okay, you have to make sure to go back to 1. 1. What's going on here? Okay. I'm getting better. Obviously you need a little bit of hang time here. What am I doing wrong? I think you have to go a little early. Yeah, it's like sending, right? Oh, there's quite a delay. I think, you know what it is? I think we might have to change the delay here. Ah, okay. So, oh, oops. So basically there's this delay time, and it won't actually jump until the release happens. So maybe let's make the delay time really small. We'll make it 1 millisecond instead of 100. So now this should be a little bit more responsive. Oh, but I'm not running anymore. What's going on here? Run. Yeah. Okay. Takes a little while to debug. There we go. 2, that's my top score yet so far. Okay, you get the idea. The point is, like, anything you can control with a key press, you can set up the classifier to work. Anyway, like, you might want to train something that doesn't involve you like doing this, because it gets quite dizzy. Let's actually change this. I want to now. How about this? Instead of doing, so we'll have the delay time be 1, and we'll say instead of, first of all, instead of that, we'll do left and right. So we'll say VK space, we'll do VK right and VK right. And then instead of doing nothing, oh yeah, that will oh Jesus. I have to stop this because it's actually typing for me. So I'm gonna stop that, and then we'll basically change, we'll do 2 to be right and 3 to be left. So now we got it. Let's train another class actually. So I'm going to clear these examples by pressing X. So that goes back to 0. Change this to 1. Go back to the video, and let's do this. So this will be 1. It will just be me. So record a little bit, and then I'll put this over here, and I'll change this to class 2 and record for a little bit. Now I'll change this to class 3. I'll put this over here, and I'll record for a little bit. And then I'll hit train. Now I'll hit run, and now it should be 1, 2, 3, 2, 1, 2, 3. So that's a lot better, right? So now we're going to do this so that when you do 2, it goes right. When you go 3, it goes left. And now let's go find the Super Mario Kart. So play Super Mario Kart online. Loading game. So what I'm going to do is have Wekinator running. So we have the inputs coming through. And now this, let's give this a shot. This may not work exactly as I expect right now. And and also, sorry, how do I turn off the? Now let's make sure that the keyboard key press thing is running. Okay, so key press is running. Wekinator is running. And now I should be able to go left and right. So we'll say let's do Mario. Okay. So now I hit the gas by pressing X, and then if I, oh, but I can't move my hands. So let's see if this, oh, and also it doesn't go fast enough. Okay, so like it's a little bit of debugging. So here's the thing. The way that the key press works is that whenever it gets a key press, it'll hit the it'll hit the left key, like press it on, delay for 1 millisecond, and then press it off. So that's actually not very good, because then it doesn't hold it for long enough. So we got to make a few changes to this, small changes. So this will say, right, only trigger of current class is different. So let's think about this for a second. I think, yeah, let's set the delay time. So let's do this. We'll make it so that instead of how it says if current class is not equal to last class, actually put a comment before this, 2 slashes, and then put a brace down here. So the reason why I'm doing this is right now the key press application has this limitation where it says only hit the key if it's different from the last time you hit the key. Sorry, if it's different from the last key. So like only hit the keyboard when you have a change. So now it'll just keep on hitting it repeatedly. So this should work a little bit better for this game application. So I'm going to or is it? let me actually, I'll move them out, and then it's still not long enough, right? It's like it takes a little bit of oh. Obviously this can be a little tricky to handle. Let's do this. We'll change the delay time to be back to 100. And let's do this again. Now it's actually turning right a little too much. Go the other way. Oh, I can't get it to get a... have to retrain the classifier. Okay, well, the point isn't to play the game very effectively. The point is to show you that, like, you might have some other ideas of things you could play. So here's another cool thing. We could do Tetris. Tetris is a good one. You can play Tetris with your face. Whoa, okay, hang on. Stop running. Does anyone have any good ideas for apps that you play online? Tetris is a good one. Should we try Tetris? Any gamers out there playing online video games? Space Invaders. Anybody have some games they want to hook this up to? So let me give you a brief rundown because I haven't. Whoa. We're going to stop this from running. Oh, I see. Yeah. So while Mario's complaining at me. Let me quickly look through the code for this. So I haven't really described exactly how this works. So this single trigger thing, I think that's it's not being used. I had to fix that. Basically, we can read through the code. This is what it says. Every time Wekinator sends a classification to keyboard OSC, it receives it here. And before, the way it did it was that we had this statement, if current class is not equal to last class. So basically it says only run this code if the classification you get is not the same as the previous one. So sometimes we want that and sometimes we don't, right? Because basically you might have a situation where you want to press a key only once to make a change, and then it'll just keep going that way. Otherwise it won't do anything at all. Now, if you're doing a race car game where you need to keep on hitting the key, you can switch this off, right? Or actually, the proper way to do this would be to use this single trigger. So you say single trigger is true. So it would basically be if single trigger and this. So now we have this flag that we can turn off. And now if we say if single trigger is false, then it will always run this even if it's not the same as the previous class. And then it goes, okay, if the class is 1, do nothing. So you have you can have a fallback, don't hit the keyboard on do nothing on current class 1. And for all of these others, you're hitting one of the keys. So right, left, you have space available, up, down. Return is another one that you could use if you want. And the way it does is that it goes, okay, key press, delay by delay time, and then release key. So it depends on how you interact with whatever program that you want, whatever website or whatever it is that your online application that you want to use, right? You may want it to hold the key, or you may want it to just tap it once, in which case you could set the delay time to be very small. Those are all basically it depends on the program that you want to use. Okay. Okay. So let's look at a few more. Oh, stop. Let's look at a few more examples let's see what else is in the Wekinator examples folder. Let's do the photo booth, and then that should be the last Wekinator example, and then we can switch gears. So the photo booth is pretty easy. The game playing thing is kind of hard, right? You have to figure out a good way to have the program interface with your interface with your with the key presser. Sorry, interface with the game that you choose or whatever it is that you want to have it use online. It doesn't have to be a game. It could be like any online application that interacts with the keyboard, or a video game that's played on your computer or whatever it is, because it's literally simulating key presses on your computer. And there's also a way to do this for the mouse as well. We don't have an example for it, but you could robot mouse. You could have both of those things interacting at the same time. There's lots of things you could do. You can imagine actually using this for like once you have mouse and key control, you can like let it go overnight if you want. So maybe your input is some data stream or something that's continuously reading from a camera outside while you're away, and then it's controlling Photoshop, let's say. So once you have control of the keyboard and mouse, there's no limit to how you can interface with your computer. And actually, like one example I did of this is I controlled, I think if I can find GoBot. Yeah. One thing I did earlier was I found an online player for playing Go, and I have a neural network that is actually playing Go for me. So what it would do is it would read the game state, and then it would make a prediction for the best move. And then I would basically it would make moves for me. Right, so this is actually like the mouse goes there automatically. So I'm having like I was playing against oh, actually no, sorry, I didn't have that. This is me moving the mouse manually, but I could have been having it like click on the internet here to like play against human players online completely automatically. What was? Black or white? I am black. Yeah. Am I? Oh yeah, I'm plus 6.5. Yeah. I think I'm playing against. Yeah, I was playing against some actual human player here. Anyway, so like there's lots of things you can do. You can play Go online, you can play chess online, and as long as you can. Sorry? The Go one? That Go one actually comes with Darknet, which is a library that I'm using for a lot of stuff. That's an open framework though, so we're not gonna look at that. Okay, so let's look at one more Wekinator example, and then we can switch gears and maybe start to lead up to that collab stuff. So I want to do the photo booth. That one is nice and easy. So let's open photo booth. I want to actually. So basically what photo booth will do is it will take a picture when it receives class 2. So here, I'm going to get out of the key press thing. Here's the photo booth. And it should be, yeah, receiving. So basically, we have this here, and we have the video 100 inputs here. And it basically, let's just open Wekinator, and it's running. What this will do is whenever it receives class 1, it will take a picture at class 2. So if I hit class 2, see, it took a picture. And it saves it. Oops. Still in here. And it saves it inside of the folder, the data here. Oh, there's these two right here. So here, let me erase those. And why doesn't it hear my shutter? So there should be. Okay, so basically, go back to Wekinator. And basically, whenever you get a 2, or as long as it doesn't match, 1, 2, takes a picture. Go back to 1, 2, and then it saves them here. So one thing that you can do is like have it only learn to take pictures of certain things. So like for example, let's retrain this. I'm going to clear the examples. You can clear the examples by pressing X. And we'll train basically this to be 1, so just everything, just me kind of around here. And then I'm going to put my phone in front of the camera, make this class 2. Oh, well, of course. And I'm going to record these examples of my phone. Stop recording, train. And now I'm going to run it. So it should only take pictures of me when I put my phone here. So we can see all those examples. Here are all the images. Although those we had before, so it's just here's the phone images. You can see it actually captures it in the middle. That's a nice little glitch. Whoa. I got my face is offset. Whoa. So one thing that Andreas did before with this application is that he trained it to recognize him when he makes a prune face. So when you do this, like that, and it'll only take a picture when you look at the camera like that. So it's a prune camera. So then you get people in the photo booth, basically like you get a bunch of pictures of them scrunching up their face. So a nice little photo booth thing. Okay. So that's basically Wekinator. Like, and I know that some of these examples are very dinky, but the whole idea is that you have a template. You have several templates, right? We have kind of 2 templates here that we worked with today. One is a generative art template. So if you can create generative graphics, you can have those graphics be controlled by inputs. And now we've only used very simple inputs like camera, but of course, like Wekinator is takes in any input that you give it, as long as it can read OSC. So for example, you can read Arduino sensors. You can read connect points, right? You can read, potentially you can read things like the leap motion sensor. You can read the face tracker data, and anything else that you can get running on your computer. Now, I have a collection of somewhat more advanced inputs that we didn't look at because we didn't look at as part of the workshop because it doesn't run on Windows, unfortunately. I didn't want to do something that half of you could use but half of you couldn't. But for those of you who are on Mac, you can check out ML4A-OFX. If you Google for ML4A-OFX, this is a collection of open frameworks applications that do somewhat more advanced things that can send OSC to Wekinator. So you'll see that, for example, if you go to releases and you download this ML4A-OFX OSC modules, there's a whole bunch of applications here that send data to Wekinator. So one is a convolutional network. So it's a replacement for the video input stream that takes 100 pixel values, which is like roughly isn't very accurate. And it replaces it with a convolutional network, which is much more sophisticated image classifier. There's also the audio classifier, which is the one that I used yesterday. Oh, there's a processing audio classifier too, so you have at least that. And there's a handful of others that do like a connect. There's a connect input reader if you have a connect. There's a leap motion one. And those are kind of the ones that you could use pretty well with, with Wekinator. So those are all available to you. And then the other template we looked at is instead of controlling generative art, controlling your keyboard. And that's pretty much unlimited. We don't have an example of using the mouse, but that's something else we could probably add to this later. So yeah, you can basically, so that's the second example, is a generative art, robot key press and generative art. And then the third one that we didn't really look at is like triggers for events. So let's say you're doing something in the physical world, you can have trigger points that find, when let's say the camera detects something, you can trigger an action to occur. That's what processing is often used for, right? It's sort of like triggering various actions to occur within your workflow. Okay, so are there any questions on Wekinator stuff? Yeah?
Just with the last thing we did, when I was running the video 100 sketch and the photo booth one, I couldn't, the canvas from the photo booth was especially great because I think the camera was using the
Yeah, this kind of happens inconsistently. Like, I can't figure out why it does in something, because I know basically like sometimes applications don't let you use the camera in two places at once. Usually I thought in processing it's kind of fine, like it does, but you might be getting a variant of that issue. Did anyone else experience that where, okay, a handful, most people didn't though, most people saw it in both applications? I can't figure out what causes it and what doesn't. Like sometimes you can only run the camera in one sketch. Other times though it seems to work okay. I'm not 100% sure. It might be which order you start them in, because I think one of them like looks for the first available camera and one of them just grabs whichever index. So that might be something to look into. I'm not 100% sure though, offhand. Okay, so any other questions on Wekinator stuff? Okay, so here's what I want to do in the last, we have about like 20 minutes or so. So tomorrow we're going to run through this, we're going to entirely switch gears and do something like more generative speaking, not something real-time or interactive. We're going to create cool generative graphics. And I'll show you, maybe at the end of today, I'll show you a video of the kind of thing that we'll be able to make. We're going to do that tomorrow, but in the meantime, I want to maybe get a head start and show you, basically do a little lecture about what neural networks see, which will kind of inform what we're going to do tomorrow. So let me quickly pull up some slides for you. This will just take me 1 second. So these are my slides. And I have to remember where I put this. Give me 1 second. It is, I have to, okay, so let's do this. Okay. So basically, I want to do a little prelude into what we're going to do tomorrow, which involves describing a few things about neural networks that we kind of glossed over on the first day. So I introduced neural networks and what they do. But there's a few interesting properties of neural networks that lets us do interesting things with them. So one thing is, and I showed you this slide on the first day, where I showed a neural network being trained, a one-layer neural network being trained, and I mentioned how, I basically mentioned how that neural networks, when you feed them a lot of images, they learn a sort of representation of those images so that you can visualize what that representation looks like. So one way of doing that is by taking the weights in the network that were learned in the process of training and visualizing them on the same sort of grid that you visualize the actual images in. And you see that the neuron, which is looking for zeros, it learns a sort of template, like a zero template, right? And you can see that here. This looks kind of like a 0. This looks like a 1. This looks a bit like a 2. 3, 4, 5, 6, 7, 8, 9. You guys can kind of see those, right? And this is what they look like summarized. Now that's simple enough because it's a one-layer neural network where the input goes directly to the output, and so the only thing that can be that the network has the capacity to learn is each of the classes themselves, right? So over here, right, we did this demo where instead of having a one-layer neural network, we had a many-layer neural network, right? So you have many layers of processing, and we talked about how in the first layer you have these filters, and they learn these activation maps or feature maps, which show the presence of all of those different patterns, right? Horizontal lines, vertical lines, diagonal lines, and so on. And as we go through the process of convolution, the patterns that it finds are more and more complex until we are able to get patterns that are so complex that they find entire objects. So for example, here we looked at one neuron which is able to find things like faces, right? So 156. Right, so that's looking for faces. Now the thing is, like, okay, how do I know it's looking for faces? Well, I'm just interpreting it, right? I say, oh, it seems to be only lighting up here for faces. And I can, that's my speculation. But it turns out that there are some more formal ways of actually showing what do these neurons look for. So one way of doing it is in this approach that was first described in 2013, where these scientists basically said, okay, what if we take 1,000 images or 10,000 images and we send them all through the network and we record their activations, and then we just save whichever parts of the images made those neurons light up the most. So they just save actual parts of real images which make those neurons light up. So here, for example, in the first layer of the network, you have 3 of these filters, right? Or 9 filters, right? And they look for very simple patterns, right? Diagonal lines, patch of green, patch of pink and green. And then for each of those weights, those filters, we save 9 parts of real images which activated those filters. So you see that in the top left cell here, you have a diagonal, it likes sort of diagonal lines, right? Whereas over here in the bottom middle here, it likes patches of green. These are actual parts of real images which maximally activated this particular filter, right? And so this particular filter is lit up whenever it sees like a patch of pink in the top left, basically, right? Now the thing is that it's hard to visualize the weights as you go through the layers of the network because they no longer make any sense. They have many channels to them, and they've gone through several layers of processing. But you can still do this experiment where you send many images to the network and you isolate a particular neuron and you ask, what images did this respond to? So if you do this in later layers, for example in the second layer here, you see that there's one neuron which likes parts of images which have parallel lines, right? Seems like vertical parallel lines here. And this part of the image likes rings, right? Or sorry, this neuron likes parts of images that have rings. These are actual photographs, and this neuron responded very highly to these ring patterns. This one responds very highly to these ring patterns. This one likes sort of horizontal, almost slightly leaning lines, right? This one right here, it likes corners, I think. I think you see very straight corners here. And in an even later layer, you have this neuron, it responds to even more complex objects. So this has repetitive patterns, right? Like lattices, right? And yeah?
When you say response, what do you mean by that mathematically?
It has a high activation. So remember in the demo where it lights up for my face, it has a lot of brightness there. That's what I mean. It got received a high activation value. Mm-hmm.
And
Yeah.
how are the features defined by user or?
They're learned by the network in training. Mm-hmm. Good questions. Any others? Right. So this one, and you see, look how much variety there is. Like in the actual, at this point, the objects are very complicated because they don't necessarily have the same colors or even the same shapes, but they're united by some high-level feature. Like this one responds to lattices, it seems like. This one responds to, I see diagonal lines going this way. This one I see wheels, right? This one I see upper bodies, right? This one's cool, it's text and barcodes. And it has text of different languages too. So it seems to be like a text neuron, right? And so forth. So this is kind of a neat technique that you can use. So now here's where the question gets really interesting. In around the same time, so a lot of this research kind of grew out of an effort to understand what these networks are doing, what is happening internally inside of them, what are they learning, and so one way of doing that is these experiments that we just saw, where you take real images and you forward them through the network, and then you isolate parts of the real images which maximally activated a particular neuron, right? But an even more interesting thing you can do is, instead of using real images, what if you say, okay, what if you pick a neuron and you say, I want to activate this neuron. What image would activate this neuron? You know what I mean? Like, okay, so here we took real photos and we just piped all of them through. And then, this neuron seems to respond to these upper bodies, right? But what if you reverse the process and you say, okay, I want to take this neuron and I want to find an image which will maximally activate it. So instead of looking through a data set, maybe I can actually find a set of pixels which maximally activates that neuron. Does that make sense? Did I explain that well? I know it's a little weird. It's like, okay, like all of these images maximally activate this neuron, but maybe you could, maybe there's a hypothetical perfect image, like a perfect image which will really activate that neuron. Like, what would be the image of all possible images which would maximally activate that neuron? So that was asked by scientists starting in, let's say, 2012, and they did these experiments where they said, okay, maybe we can synthesize images which maximally activate a particular neuron. So one neuron that you might want to activate is the classification neuron that has the label assigned to it. So for example, they have this data set that has things like washing machines and computer keyboards and kit foxes and so on. And they go, okay, can we synthesize an image which will convince this neural network that it's looking at a washing machine, right? And it looks kind of like this, right? Now it doesn't look terribly impressive, right? This was 2011. But you can kind of see something washing machine-like happening here. Or maybe okay, do you see Kid Fox faces? Bell pepper looks pretty convincing. Do you see the shape of the bell pepper? Lemons, limousine, ostrich.
So you're just looking at the last layer of the.
This one here is the last layer, yeah.
Is it? I thought that this is the image that was synthesized in order to drive the image.
Exactly, yeah, yeah.
Is with the sort of gradient descent or genetic algorithm, or how do you arrive at?
So this is learned through gradient descent. So what they would do is this. So I mentioned gradient descent on the first day. Gradient descent is how a neural network is trained. You give it a lot of images, and you get the correct labels, and then you use gradient descent to train to get the correct weights. So here they actually do the process. They do gradient descent, holding the weights fixed, but do gradient descent on the pixels. Now we haven't really for most of you may not have understood that because we didn't really talk about that in the first day in much length. So that won't make sense to you. So you don't have to worry about the exact process. The point is there is a process by which you can arrive at an optimal set of pixels which maximally activates a particular neuron.
It will be a local optimum.
Sorry?
It will be a local minimum.
A local, yes.
Because so you basically start off with just noise image.
Yeah.
The grainy noise image, and then you keep tweaking it to make the neuron happier and happier.
Exactly. Yeah.
And which noise you start off with may make a difference.
Yes.
You might well end up with other.
It's totally stochastic. I mean, it's basically like if you do this 1,000 times, you'll get 1,000 different images.
But they all look a little bit lemony.
Sorry?
They look a little bit limousine-y or something. If I did it again for the limousine image, I might have one that has to wheel somewhere else.
Yes, exactly.
Just another local minimum that would be just as nicely locally minimal.
Right. Right.
I'd like to do that.
If the image is small enough, you can just try every combination.
Well, so yes, but you know how many pixels there would have to be? That like okay, so
So in a 10 by 10,
if it's 10 by 10,
it's
so if you have 10 by 10 pixels,
256 times 256 to the 10, right?
exactly. This is how many
That's
possible images
that's
there are.
100. Oh, 10 by 10.
10 by 10, yeah. And actually, really, it's color. So it's this.
Right.
So forget about it. Like a 10, like the number of this is the number of possible 10 by 10 pixel images.
So there's that piece by John Simon, which is
Every image ever, right? And it's going to take 10 gazillion years, yeah. So basically, like you can't try every possible image because it'll take all the computers in the world like a gazillion years to try every possible image because there's so many possible images that. So the number of atoms in the universe is 10 to the 80th. The number of 5 by 5 by 3. So the number of 5 by 5 pixel images is this many. Like it's 10 to the 180th. So there's way more there's way more 5 by 5 pixel images than there are atoms in the universe. So that's really unintuitive to people, but it's actually completely true. Yeah. So yeah, so that's not gonna work, basically.
Any local minimizing algorithm will work for this, like genetic evolution.
You could, I mean, people have tried to use genetic algorithms to train neural networks instead of gradient descent. It turns out the gradient descent works better, but like maybe that'll change. You know, there's people who want to use want to use genetic algorithms instead. But in any case, like the point is, like for everyone else who may not have really understood that discussion, like there is some algorithm which finds a set of pixels in a reasonable amount of time, which has the desired property that it maximally activates a particular neuron. Now this is from like 7 or 8 years ago. It doesn't look that good, right? There have been improvements to this technique. So let's look. This is actually one of the first times that machine learning made a big viral thing happen, basically. So this is from 2012, and there was I don't know if anyone remembers this in 2012, but like Google was in the news for generating the cat neuron, right? They basically downloaded like all of YouTube and then did this technique to synthesize an image of a cat, and this was the Google cat, the optimal stimulus for the cat neuron inside their classifier. So this was big news in 2012, and then in 2015 there was this. Now this is basically like mid 2015. So I think a lot of you saw this. This is Deep Dream, right? So people are familiar with Deep Dream, right? How many people have heard of Deep Dream? Right? So the idea of Deep Dream was exactly what I just described, except they had figured out some good tricks to make it synthesize a little better. We're not going to talk about some of them. They're just like little tweaks to regularize the pixels so you don't get so much high frequency dust and so on. And then basically they showed this. They had this blog post online. This is in 2015, where they describe. This is the same exact technique, except it looks a lot better now, right? So here you see like anemone fish, banana, parachute. Notice something about the parachute. There's like a human attached to it, and several other parachutes. So because if you have a lot of images of parachutes, they probably have people attached to them, and so it doesn't disentangle those two things, right?
Yeah, it's important to note that this is for a particular training set.
Exactly.
Not like the abstract computational
Right.
representation of parachutes.
Right. So there's a data set of images that are labeled parachute, and many of those have. Yeah.
Like if you had face and all your tests were, for example, white people, you'd get a white person's face.
Yes.
And then those other colors wouldn't be identified as people's faces.
Well, we're not identifying, right? We're just synthesizing. So.
Well, either way, right? Like, because if you try to classify with that.
Yeah, sure. If you were trying to classify with that neural network, it wouldn't recognize anything that wasn't labeled as part of that class. So, exactly.
I don't think that's a given, because you don't know what your feature detectors generalize on. They may be much more interested in shape than in color.
Well, sure, right, exactly. So it's not clear. Like the more examples it receives of the thing that you want it to be able to recognize, the better it will do at doing that.
Exactly. So if you have enough white faces that are filmed under blue light and white light and green light, it makes us learn that actually color is not nearly as important as what
Sure,
you have a
sure.
in the nose.
Yeah. So I mean, there's no answer here. It's like it may do worse and it may not. It's like something you have to test for.
Does this give you insight into the biases of this reverse, like?
I'd say so. Yeah. I mean, people. This thing is not just used for art. It's used for a lot of stuff. So there's this whole field of machine learning called adversarial training, which is the idea of trying to fool neural networks, and it's very closely related to what we're looking at. In any case, so we just have a few minutes left, so I want to just finish the slides, and then basically we're going to be making these tomorrow. So basically, like a few days after this, there was a post on Reddit, or actually just before the blog post, someone posted this image onto Reddit and wrote image generated by a convolutional network. And it was this weird slug looking thing. Did anyone see this? A few people, right? So this was submitted anonymously on Reddit, and then people were like, what the hell is this, right? And actually it turns out they never figured out who did it. It was some employee at Google who leaked it anonymously. Anyway, a few days afterwards, Google released that blog post, this one, and then they described this technique called Deep Dream. So Deep Dream is basically exactly what we just looked at, except it has a few innovations. So before, in this process, you go, okay, you have a particular neuron and you go, I want to maximally activate this neuron, which means that I want the network to have the following output: 0 for everything and 1 for this neuron, right? And then you synthesize an image, right? And you start, as you mentioned, you start with an image of random noise. And then you update the pixels until it finds an image which maximally activates a particular neuron. So that's this process. Deep Dream is almost the exact same thing, except what it does is it doesn't start with a random image. It starts with any image that you give it, and it says, okay, instead of you choosing a neuron to target, what it does is instead it takes the image, it finds the outputs, it finds the network's output, the activations, and then it changes the pixels to make all of the activations higher. Right? So basically its target isn't 0, 0, 0, 0, and 1 for some target class. Its target is to make the activations all higher. So what it does is it ends up finding patterns and enhancing them. And you can choose a particular layer that you want to do that on. So here, if you choose one of the early layers, which has things like edges, then you end up synthesizing. You enhance those edges, basically. They're all just edges and patterns like this. If you enhance later layers, you find entire objects. Admiral dog, pig snail, camel bird, dogfish. That's a later layer. So then some of the researchers began to use this to make art. And one of the first ones, I think, to do this was one of the original researchers here, Mike Tyka, who is an engineer at Google, researcher at Google, who would apply the deep dream technique to actual random noise and generate these crazy landscapes and neural landscapes, which resonate sort of real life but are completely synthetic, right? So basically, they released their code online called Deep Dream, and then everyone could download the code and use it on their own images. So when I saw this, I'd never seen this before, so I was really excited. And so I downloaded it, and I started using Deep Dream on my own images, right? So here's fireworks being deep dreamed. And then I started making videos with it, right? So this technique will do the deep dream technique, and then we're going to describe this in more detail tomorrow because we're actually going to make stuff like this. Basically, the idea is you take an image of random noise, you deep dream it, which means doing this process that I described, enhancing all of its activations. And of course, it's random noise, so it's not going to find anything real. But the thing is, no matter what, a neural network will always have some output, right? And so if you run this technique and you enhance the output, it will create if you do it repeatedly, it will create patterns. And then to make this sort of zoom in thing, you take the image that I created and you crop it. You get rid of the edge. And then you resize it so that it's the size of the original. So it's like a zoom in effect. And then you just do this repeatedly, and it basically just generates this stuff endlessly for however long you want to run it, right? And it has lots of this was the original implementation of this. It has lots of diversity. You can choose different layers to try to optimize, and we'll talk about all these things in more detail tomorrow. But basically, you can create all this kind of stuff. And there was just more people, like Mike Tyka started doing artworks with it, finding different ways of, okay, this is a pelican. It's trying to optimize the pelican class, and basically leading up to this. So I don't know, I want to actually end right here, and I want to show you basically the kind of thing we'll be doing is this. So I don't remember if I showed this to you on the first day, did I? Did you see this video? Okay. So this is a video that I recently submitted to NIPS conference, which is the main machine learning conference. They had of the year. They have a art exhibit now. This was the first year of it, and this is using the technique basically to just create visuals, right? And the notebook that we started looking through yesterday shows how to do a relatively simple version of this, and we're going to basically step through it tomorrow, and we're going to make some of this stuff, and we're going to use Google's own servers to compute it, which is really, really fun. So there's various things that I haven't described yet that are part of this video. So you see it moving in various ways, and that's all depending on how you change the canvas. So the zoom in technique is cropping, but you can also do things like shifting or rotating or distorting with Perlin noise, right? Or expanding out from the center. So all of those things are things that you can do to the canvas, which require nothing more than basic geometry, understanding of geometry. And then the last thing that I do here is running multiple classes and masking them, so multiplying them. So that's Jan LeCun. Now, first of all, the video that you're looking at is HD, and it's video, so it's 3 minutes long. So there's 60, so there's, what is that, 180 seconds, so there's like 4,000 frames. and each frame takes like 10 minutes. So to produce this video, it took like days of computation. So we're not going to be able to easily make video tomorrow. We're just going to make the basic thing, and then after that, to make video, you'll be on your own. Because that takes a lot more computation than we'll be able to have tomorrow. That's Fei Fei Li, who's at Stanford. But basically, like, this is the technique that we're going to try to look at tomorrow. And depending on how much time we have, we might look at something like style transfer as well. So that's a little cliffhanger for you, so you guys can kind of have an idea of what you want to do. Yeah. So yeah, we're done for today. So yeah, until tomorrow.